Good afternoon, everyone. Today we will be giving Aero Design's final presentation. Today we will discuss the progress of our technical departments and the different aircraft. We will start with the aircraft performance department, then structure and materials, electronics and software, then the micro class, regular class, and finally the advanced class. The main goal of the aircraft performance department is to ensure a successful and stable flight. This is done studying aerodynamic behavior to optimize the aircraft's exterior geometry along with its control surfaces. We implemented tools like a normalized decision matrix and configuration comparisons. On top of that, our department oversaw visual critique of the airplane's behavior at each test flight by taking into consideration dynamic protocols like takeoff, climb, cruise, stability, descent, and landing for possible improvements with redesigned procedures and iterations. To validate our designs before manufacturing them, we conducted a series of analyses like simulating the aircraft inside a digital wind tunnel using CFD like StarCCM or ANSYS flooring. On top of that, we also tested for static and dynamic stability to ensure it's positive in lateral and longitudinal modes.
Good afternoon, everyone. My name is Hector Arcelay. I'm the Structures Department leader, and I'll be telling you about what we did in the Structures Department during this semester. Our design process began since the summer, where Structures Department members were assigned each to different disciplines of structural analysis. Various members of each aircraft were assigned to different research topics so that there was at least one specialist of each topic in each aircraft. First, we studied the mechanical properties of various possible woods, 3D printing filaments, and other carbon fibers that we could use in our aircraft. In addition to this, we looked into how to properly carry out mechanical calculations for wing spars, booms, and landing gears using different materials, how to properly confirm these calculations using finite element analysis. The load analysis for the wing spars is simplified into only a distributed load of the lift produced by the wing. The distributed load can be found using Schrenk's approximation. This method uses values of aircraft speed, loading factor, two-dimensional lift coefficients, and the weight of the wing to approximate the lift generated through the ribs along the wing. The load analysis for the booms comes down to the downforce produced by the empennage, which can also be calculated using Schrenk's approximation. These values were confirmed with the aircraft performance department using CFDs. After this, we used the properties for mechanical calculations for spar and boom sizing. The materials that most favored our airplanes are orthotropic or anisotropic materials. And while we can assume the material to be isotropic using data found from testing online, we went the extra mile to find a more precise way of proving our dimension selection was correct. The wood group members created a new material library and workbench that includes the properties of wood along the three axes, enabling them to model wood in workbench. The carbon fiber group members were successful in modeling our carbon fiber spars and booms using ANSYS ACP software, which essentially allows them to manufacture a carbon fiber part ply by ply with their respective angles of orientation. I'm very proud to say the results of the analysis provide negligible discrepancies with less than 2% of margins of error. Furthermore, the topology research group, using ANSYS topology software, were able to create finite element analysis guided weight reductions. The ANSYS software analyzes the stress a given part experiences and shows where it is safe to take off material without compromising the structural integrity of the part. Internal structures for wings and fuselage consist primarily of ribs and stringers to keep the aerodynamic shape of the aircraft, and we only employ solid structures for landing gear and motor attachments. And this has been a general summary of what we did in the structures department during this semester. I'll leave you guys with the electronics department leader.
The electronics department has been working with the aircraft system circuit design and integration, the propulsion system testing, and this year we are using anti-gravity motors for the regular and advanced class with carbon fiber propellers.
Good afternoon. My name is Rodrigo Pagan. I am a Structure and Materials Department member of the Microclass aircraft, and today I will be presenting the work done throughout the Fall 22 semester. Now I will be talking about the mission statement. Firstly, I will be talking about last year's mission, which was to take off from an 8-foot-long platform, and for the aircraft there was a wingspan limitation of 48 inches. And an electronic configuration limitation, or the power limiter, of 450 watts. Additionally, another part of our mission is that we have to load pizza boxes. It could be 12 by 12 by 2 inches and metal payload. For this year, the rules were not supposed to change. However, the composition decided to modify the rules last September. The change was a drastic one, decreasing the wingspan from 48 inches to 36 inches, a 12-inch reduction. This change was greatly set back the team since a preliminary design was brought up last year with the 48-inch wingspan. Nonetheless, we were able to deliver a new design for the new dimensions. In this slide, I will be talking about the aircraft's design, specifications, and static stability. Here on the right side, you can see some pictures of the aircraft assembly. As you can see, the big challenge for the design of this airplane is mostly to try to have a good aerodynamic design, a fast airplane, and an effective structural optimization in terms of weight. These things are the pillars to be able to complete the 8-foot takeoff from the platform. Here we can see the aircraft performance specifications of the plane on the left side in the table, where we can highlight that it has a relatively high Mach thanks to the drastic sweep of 32 degrees that the design has. In addition, the ideal center of gravity of the plane is 11.68 inches from the leading edge. However, probably some of these values will be changing in the next few days, and we will see later why. We can also see in this slide what the internal structure of the airplane is, which was designed so that the plane weighed approximately a maximum of 5 pounds with all its components. It is very important to achieve this weight because if the aircraft weighs more than a few ounces, it could affect the takeoff performance. In terms of the manufacturing process, it was somewhat complicated, but all the improvements are already being worked on to optimize this process and make this easier for the second test flight. In the electronics department, there were not many changes in the configuration compared to last year, but there was an excellent job done on the part of the members in the search to understand and optimize the performance of the motor and the weight of each component, which is looking for the components that do their job effectively but being as light as possible as well. In addition, this year's members got an engine propeller configuration that used an engine that weighs 3 times less than last year's, and a much more efficient carbon fiber propeller than APC's. Last November, we were able to carry out our first test flight, where we obtained enough data to help us analyze our current design in order to optimize the design as well as the manufacturing processes and materials. Let's watch this video to elaborate on this. Once you're done watching the video, here I will explain what happened during the test flight. The plane goes down due to a structural failure in the motor mount. This was because we did not have time to send the motor mount to weld, so we went to plan B, which was to glue it, but it was unsuccessful, as you clearly saw. However, the plane had a successful takeoff, and despite what happened, we were able to get a lot of additional information. For example, we deduced that the quick takeoff performance of the plane was affected thanks to the fact that the downforce made by the empennage was too much, which led the plane having to reach a higher speed than expected in order to create the necessary lift to take off. This is because the plane managed to take off only when the horizontal control surface was deactivated, which was activated throughout the takeoff trajectory. However, we think that since our horizontal is an upside down airfoil already in its normal position, it is creating downforce, so it might not be necessary to activate the elevator to perform the takeoff, which was the opposite of what was happening here. We will confirm this in the next test flight, which we hope will be before the end of the year or at the beginning of January. For future work, we must replace the balsa main spar of the aircraft with a carbon fiber one in order to improve its rigidity without greatly affecting the weight. The main spar is basically one of the most important parts of the aircraft because here it receives the loading of the lift of the wings, the booms, and the rear landing. We are also in the process of redesigning the empennage to have a better takeoff performance data and to be able to confirm our hypothesis from the past test flight regarding the horizontal. We were also in the weight optimization phase, reducing the weight of some areas that we noticed could be improved and using better materials in other parts that are necessary. All these optimizations and modifications that I have just mentioned will be tested on our next test flight, which is pending. That will be all for the presentation. Thank you for your attention and have a good day.
Now we will be going over the regular class aircraft. This year, the regular class was subject to a complete rule change. Previous to the arrival of the rules in September, the team focused on thorough research in all departments to ensure a plan for any new change. Once the rules arrived, the mission score formula was evaluated considering the following factors: takeoff in 100 feet or less, wingspan, component sectioning, metallic payload, and maximum total weight. This year aircraft has a limit of 100 feet takeoff limit, a minimum wingspan of 120 inches and a maximum of 216 inches. Bundle assembly components cannot exceed 48 inches. It will carry regular box metallic payload and has a maximum weight of 55 pounds in total. Here you can see the scoring equation. This equation was analyzed to determine the best configuration for the aircraft, and based on this analysis it was determined that how we could get more points is by having the maximum wingspan. So that is why we worked on the design that we will be showing now. Here you can see all the components, the CAD for the different components of the aircraft. You have the empennage, the fuselage, then below that the wings. The complete specs of the aircraft are displayed, showing a great static margin of stability with a relatively high aspect ratio to achieve better aerodynamic performance. The slide dihedral was added to support the structural design since the wings have a combined airfoil design. The fuselage will be mainly held up by aluminum skeleton since the booms will go all the way to the front to provide a structural sound design. The landing gear for the aircraft will be acquired from a manufacturer to ensure correct support at a 3-point landing gear. The empennage will be 80 inches long. This length, core, and height are this large since they were the best option to correctly locate the center of gravity while still maintaining a good longitudinal stability. This will compromise a bit of the lateral stability, but will compensate with a stable flight. As a final view of the aircraft, the full assembly is shown here. The plane will be sectioned as seen in 4 sections of 42 inches and a section of 48 inches, which is the limit. The empennage will be divided into 3 sections of 27 inches. The booms will also be modular to comply with the section of 48-inch maximum rule. The plane is estimated to lift 55 pounds of total weight while carrying approximately 28 pounds of payload in 97 feet, achieving the desired performance. For future work, we will be finishing the manufacturing that has started, and we will have our first test flight. Now we will be going over the progress of the advanced class aircraft. This year's advanced aircraft has to take off from a 400 feet runway, has a 120 wingspan limit, needs to use a 750 watt power limiter. The payload is water, must deploy a power autonomous delivery aircraft named PATA to land on a random pinpoint. and every successful pad landing will deliver parts to assemble a ground transportation vehicle that will transport the water from the primary aircraft from one location to another. In this slide, you can see the scoring equation given by the competition and the equation for the bonus. This equation was analyzed to then determine the optimal configuration in terms of the payload that we were going to be taking in water and the points that we could get from that. This year's aircraft will have a blended wing concept and a pie-tail configuration. Here you can see the final airplane design. Here you can see the CADs for the different components. First we have the wings, then the fuselage, and then the empennage. And some of the most important parameters would be the wingspan of 120 inches, the center of gravity, which is placed on 17.7 inches, and the wings incident angle, which is 2 degrees, and the moment arm, which is 67 inches. Like every year and the other aircrafts, this aircraft was manufactured in about 2 weeks. First we assemble the structure, then put it on the electronics and the coating, and on the right you can see the final aircraft at the test flight.
Following up with the PADA and DTV design, also known as the Powered Autonomous Delivery Aircraft and Ground Transport Vehicle, throughout the semester, stability analysis were done in order to ensure our design parameters would be optimal for flight testing. However, as you can see from the photos in the slide, the first picture on the top left was our first prototype, and our actual prototype is the one on the right. For the ground vehicle, aka the GTV, the ballast fuselage structure as well as its payload will become said vehicle as the photo below. For future work, in the month of December, some design changes will be done in order to improve the structural integrity to manufacture and finally test with a full mission flight with the software implemented, as well as with the help of our fellow partners of software, which will be discussed after this slide. Thank you.
Three important things that the software department will be implementing on the primary aircrafts are airspeed sensors integrated. Here you can see how they're being calibrated. We will also be using the PixRacer Pro to get data and log the sensors data, and also replay the flight path. This will support stabilization mode. And finally, a gimbal which is being set up and calibrated. This will help the aircraft do all the required part of the mission in terms of collecting data, showing the data on the screen, having a better flight, and also helping the PADA land on the required location.
Si sube, tiene que bajar. Si baja, tiene que subir.
Wow.
Ya está.
Ya, vamos.
The PADA then uses the PixRacer sensors data to stabilize itself, and with just roll and pitch, it will land on the desired location. The software department has also been helping with other aspects of the team, like the website. We now have the updated URL with the new team's name, and the website is up to date. We also had been working on Airflow's Python script. This facilitates Airflow calculations and have assisted in providing algorithmic assistance to other departments. For future work, we will be integrating the gimbal to the primary aircraft. We will complete the PATA manufacture and test flight, and we will run a test flight with all the systems. Thank you everyone, and now we are open for questions.